We left off on Friday talking about the law of constant proportions. And we used an example of sodium fluoride. And basically what the law of constant proportion says is that if you have a pure sample of any compound, the ratio of the atoms in that compound is going to be a small whole number ratio, and it's going to be the same no matter what the source of the compound is. All right. So let's do another example of that before we move on to the law of multiple proportions, which we'll talk about today. So this is man, we through January already. Good Lord. 31, 22. Man, that's crazy. All right. So let's take this, and apply it to another example. Let's say we have and the key word to these constant proportion questions is if. Like you're going to see that term, if you have 42 grams, and that's again part of your strategy in identifying what to do with a problem is to understand how it's being asked. All right, so 42 grams of hydrogen. Sorry about that. Is in a sample, a pure sample. That's important too, because the law is based on pure compounds, right, or pure substances. All right, so in a pure sample of CH4. Right? The question now is how many grams of carbon are present, right? So with CH4, let me break that. This is a compound called methane. We're going to talk more about this. It is considered organic, not in the sense of organic, like when you buy food that's considered organic, that's totally different. This is an organic compound in that it is a carbon-based compound. Right, we'll talk more about that later. Right, so the key is to, number one, with these constant composition problems, is to find the periodic ratio from the periodic table, right? That ratio is what we use to interconvert between the atoms that make up a particular compound to figure out how much of one is present or how much of the other is present. So we need that. So for we're going to find the periodic ratio. All right, so let's go to somebody pull up the periodic table and tell me what the atomic mass of hydrogen is. We did this already, but this is just for repetition.
One.
One AMU, right? So hydrogen. And what about carbon?
12.
12. Sorry. Right? So if we have a molecule of CH4, the ratio is going to be 4 times 1 AMU for hydrogen, because we have to take into account that subscript is telling us how many hydrogens are present, right? So 4 times that, and then 1 times 12 AMU for carbon. So this is going to be our ratio. So it's going to be, we can now say that it is for this compound, for methane, 4 grams of hydrogen is equal to 12 grams of carbon. So anytime you find a sample of methane, this is going to be the ratio by mass of hydrogen to carbon. Once we find that out, we can interconvert, because now we can use that as a conversion factor. So now let's go to the second phase of this solution, solving this problem. So use the ratio Well, let me not say that. Use it as a conversion factor. Let me say it that way. So what I'm trying to do is give you a strategy to attack these problems. So when you see it on the exam, you have a way of attacking the problem because you know what it's asking for. Like once you figure out, hey, okay, this is a constant composition problem. This is my strategy. First thing I need to do is get the periodic ratio. Then I need to go back and look at the formula that I have and see what the ratio is there. So in this case, it's 4 hydrogens and 1 carbon. So I take that into account in my ratio. All right. So now I can use that ratio as a conversion factor. So now if I had 42 grams of hydrogen in that sample of methane, it's sample specific, right? Times, what do I put in the top if I'm looking for carbon?
Carbon.
Carbon in the top, which from my ratio here is 12 grams of carbon over what? 4 grams of hydrogen. Is that right?
Yes, sir.
All right. So can somebody calculate that real quick? It's really gonna be like 42 times 3, because the 4 and the 12, you can reduce that down, but we leave it as it is. We don't reduce it because we want to show the ratio. But we can
I
show
got 126.
126 grams, good, of carbon. So in this sample of methane that contained 42 grams of hydrogen, there are 126 grams of carbon. What won't ever change is the ratio for the compound, right? That's the law of constant proportion, that this ratio is going to be the same no matter where you find this sample of methane. Mars, Jupiter, Earth, cow pasture, doesn't matter. What will change, and this is based on the mass. So if the mass of hydrogen is different, like if you have a bigger sample, then you can expect that the amount of carbon is also going to change. So those masses can change based on what the problem is. But what won't change is how we find that ratio, which is we use the periodic table to get the atomic masses, and then we use those atomic masses to show the proportion between one atom and another atom in that compound. Does that make sense? Any questions about that? So that's our strategy. Find the periodic ratio and determine what the ratio is between the 2 atoms in the compound, or between the atoms in the compound, and then use that ratio as a conversion factor. And as you can imagine, you can turn this around, right? You can, if you have 126 grams of carbon, you can go back and find how much hydrogen is present, all based on that ratio. So yeah, it's a so this law of constant proportion, once you know the ratio, that's your conversion factor to find out what proportion the other atom in the compound is, that you're looking for. All right, we're gonna do more of this on Thursday, but now, well, before we jump into multiple proportions, are there any questions about anything about this question? All right, and let's go back and examine this question. So it gave us 42 grams of hydrogen. It gave us the molecular formula of CH4, and it asked us how many grams. So this is what we're looking for, how many grams of carbon, right? And again, it's asking this word or the word if is it's very telling for these types of problems. It says, if this amount of hydrogen is in a pure sample, that's another giveaway telling you that you're dealing with constant proportions. If you have this in a pure sample of CH4, how many grams of carbon are present? Right. So those are like some buzzwords that you look for when you're solving these types of problems. All right. Let's go to the next topic. We'll just go to a new page, and let's talk about the law of multiple proportions. All right, it's a little bit different because the law of constant proportions is just dealing with a pure sample of one compound. But sometimes you have elements that can combine, the same exact elements can combine to give you multiple compounds, right? So let's look at that. So if you have so let me put that here. Sometimes let me make this a little bit as plain as I can. So sometimes the same elements can combine to give you multiple compounds. So they can combine in different ways. Right. So sometimes the same elements can combine in multiple ways to give you different compounds. All right. And the reason why that's important is because unlike the law of constant proportions, when the same atoms combine different ways to give you different compounds, you're going to get two different products. And so because of that, right, the ratios may be a little bit different from one product to the next. So you have to have a way of dealing with that, right? So what this law of multiple proportions tells us is if you have a fixed mass of one of those elements, right? The ratios of the other element, the second element that's used to make a compound, will always be reducible to small whole number ratios. I know that sounds like a lot, but when we look at the example, I'm going to make that a little plainer. So if you have a fixed mass, usually we'll take this fixed mass as 1 gram. So I'm gonna show you that we're gonna reduce down the ratio so that one of those elements in that compound is 1 gram. And the other one will be whatever we make it to be. All right. So you got a fixed mass of one of the elements in a compound. So a fixed mass of one element in a compound. Then the ratios of the second element. Notice I said ratios in plural because again, you can make more than one compound with the same exact atoms, right? So the ratios of the second element will be small whole number ratios. I know this is a lot, right? So you can reduce those ratios to small whole numbers. All right, and this sounds like a lot, but when we see it in practice, it'll make more sense. All right, go ahead, Amaya.
After a fixed mass, is that a 1 gram in
Yeah,
parentheses?
1G. So
And what
normally
is, go ahead.
that's going to be our strategy. When we have two elements, we're going to make one of them 1 gram relative to the other one. And that's how we're going to solve these problems, by reducing one of the two elements in a compound and making it a gram. That's our fixed mass. And by doing that, that's going to allow us to say that any other compound made from these same two elements, we can take the second element and make a mass ratio with that, and the mass of a second compound that's made from the same atoms, and we're going to get a whole number ratio. Right? I know it's very convoluted, but when we look at it on paper, it'll be a little bit different, a little clearer. So you always want to have that fixed mass of 1 gram. That's part of the strategy of solving these problems. All right. The other part of it is recognizing that if you have multiple compounds from the same group of atoms, that every compound is different and is going to have a different ratio of one atom to the other. So let me give you an example of what I mean by this, right? And then we're going to work through a couple of examples with this law of multiple proportions. Anybody still writing down the definition before I scroll up?
What does it say before the ratios? I don't know what that word says.
Right here,
Like-
the.
Oh, I thought it was H.
Yeah, my bad.
Oh, before that, like before the ratios, what's that?
It's then.
Oh, okay. Thank you.
Sorry about that. When I get excited, I write like in chicken scratch. And when I'm not excited, I write in chicken scratch. So either way, it's gonna be chicken scratch. So anytime there's some word that you need to interpretation for, because it looks like a foreign language, just say so. All right. So let me show you an example of what it means to be able to make multiple compounds from the same group of elements or the same group of atoms. So let's say we have copper and chlorine. All right. You can combine these in two ways. You can make copper chloride, or you can make copper dichloride. Both of these are totally different compounds. Matter of fact, let's look up. Let me switch over and open up a window in my browser, because I want you to see that they're not the same. That's one of the key things, is that when these atoms combine in different ways with these different ratios, right, you get totally different compounds. Let me share my web browser. Can y'all see that?
Yes.
All right. So if you look right here, this is an example of, notice it says copper 1 chloride. We're going to talk about naming and all that stuff. But these two compounds that we can get, CuCl and CuCl2, are the reason why we get those is because of the oxidation number on copper. Copper can be, and I'm going to show you that in a second, it can be +1 or it can be +2. Look at the difference, right? This is copper 1 chloride. Look at the color, how it's kind of like a neon type of yellowish green compound. And then if you make copper 2 chloride, let's look that up. Look at the difference in color. Totally different compound, right? Different reactivity, different everything, right? So you have, but the base elements are copper and chlorine, right? So when we talk about these elements combining to make different compounds, when you combine those elements in different ways, you're going to get different things, right? Different chemical properties, different physical properties, everything, right? So this is based on the oxidation number of copper, right? Remember when we talked the other day a little bit about nomenclature, and I said that you would use the crisscross method to write out the molecular formula for some of these compounds, right? So here, if we had copper +1 and chlorine is -1, we would simply crisscross the charges, and then we would get CuCl. But if the oxidation number, which is the charge on copper, is different, then you're gonna get something different, because this is Cu to be 2+, and then Cl -1, which doesn't change. So when we crisscross those, we get CuCl2, right? The 2 subscript goes down where chlorine is, and the 1 subscript ends up where copper is. So anytime you don't see a number down here in the subscript, it's understood to be 1. Right? If there's no number present, then it's understood to be 1. And that's for any formula, any molecular formula, any compound, whatever. If you don't see a number in the subscript, everything is understood to be 1. If you see a number, then it is that number, right? So the fact that copper and chlorine can combine to give you 2 totally different compounds means that we have to have a way of dealing with this in terms of mass ratios and in terms of how these elements or atoms combine to give you these compounds. So that's where the law of constant multiple proportions comes in, because you have to have a way of dealing with that. So let's look at an example, because the way that it's written in the book, I don't like it. I don't like how it shows the ratios. And so we're going to do it a little bit differently here. All right. So let's say we have this example here, where we have carbon and oxygen. Right. You know that carbon this can give you CO, carbon monoxide. Everybody has heard of this, right? Colorless gas. You ever seen somebody in a movie take the water hose and hook it up to the exhaust and put it in the car? Y'all seen The Equalizer? Didn't he do that to somebody? Denzel Washington. Anybody seen that movie?
Which movie by Denzel?
The Equalizer.
Yeah, I've seen it.
Oh, heck yeah.
Didn't he do this to one of the people he was trying to get back at? He took a water hose and stuck it in the exhaust pipe of the guy's car and put the water hose in the window and rolled the windows up.
Yep.
Yeah, that's because the exhaust contains carbon monoxide. Carbon monoxide actually looks like this. It's carbon triple bonded to oxygen with a pair of electrons on each atom. And this is negative and this is positive, so the whole thing is neutral. But the reason this kills you is because it mimics the structure of oxygen, which looks like this. It's also linear. So carbon monoxide can bond to your hemoglobin just like oxygen does, but you don't get the oxygen. So you end up suffocating, right? So that's carbon monoxide. But then if you take carbon and oxygen, you can also combine them like this and get carbon dioxide, which is a greenhouse gas. Everybody knows it's released absorbed by plants as they, filter out carbon dioxide from the atmosphere and give off oxygen. And when we breathe out carbon dioxide and we take in oxygen. So, right, this is carbon dioxide. Not nearly as lethal as carbon monoxide. Still linear. It actually looks like this. If y'all remember from when we first started talked a little bit about bonds and stuff like that. There's a double bond on each side of carbon. And then up here, this is a triple bond between carbon and oxygen, right? Two totally different compounds. Right? So those can combine in those two atoms can combine in different ways to give you different compounds. And so the law of multiple proportion says that the ratio of, let's say if carbon is the first atom, the ratios of oxygen and carbon monoxide and carbon dioxide ought to be reducible to a small whole number ratio. So let's see if we can prove that. So again, let's take carbon monoxide and let's get the periodic table ratio. Somebody look that up. Carbon and oxygen. The masses, the atomic masses.
12 and 16.
Good. So 12 AMU for carbon, 16 AMU for oxygen. And so what that translates to is my ratio of carbon to oxygen, just like we did with constant proportions. 12 grams of carbon is equal to 16 grams of oxygen. Now, the strategy for this law of multiple proportions, because we got other compounds that we can make from these two atoms, is to make one of those fixed. So let's make the carbon fixed. So 1 gram. So we're gonna make one of those atoms fixed. That is, make it 1 gram. So let's make carbon. So we're gonna divide both sides by 12. So 1 G of carbon is gonna be 16 over 12 grams of oxygen, or 1.33 grams of oxygen. Can somebody check that calculation? 16 divided by 12.
That's right.
Okay. So this part right here is similar to what we did for constant proportions, right? This will always be the ratio of carbon to oxygen in a sample of carbon monoxide. All right. But now we want to compare this to carbon dioxide. So let's do that on the other side. So let's say CO2. And we know the ratio here is 12 AMU. Is that right? That doesn't change. Let me fix that before I get a complaint to the dean about my handwriting, MU, and then this is 16 AMU, right? But because of the subscript 2 on oxygen, we have to take that into account. So this is literally 2 times 16. Everybody following that? Because of this subscript right here. I got 2 oxygens. So by mass, I have to include them both. So this is going to be 12 G of carbon is going to be for a sample of carbon dioxide, 32 grams of oxygen. Yes or no for this sample?
Yes.
Okay. So now let's see what the ratio is, right? We want to, again, get one of them is going to be fixed. So we're just going to pick this one, right? So we're going to divide both sides. And this works either way. if you pick 32, you're gonna get a fractional number, but the ratio is still gonna equal out, so it's fine. But here, we're gonna take this and divide both sides by 12. So this is 1 gram of carbon is what? Somebody calculate that. It's 2 point something. Is that right? 2.67.
Yes, sir.
All right, grams of oxygen. So that's my ratio for CO2. Now, in order to find out if the law of multiple proportions is true, I need to compare the mass from CO2 to the mass from CO, the masses of oxygen, because the law says that the second atom in the molecule, if we got a fixed mass of the first atom, the ratios of the second atom should give me some small whole number ratio, right? So now I need to compare. Right, so I need to compare the masses of oxygen in each compound to check the ratio. All right, and it's important here that you don't reduce, because you want it to stay as a ratio. So you don't want it to be a fraction in this case. All right, and this is all based again on the constant ratio of carbon to oxygen. But the second atom in that other compound that can be formed, you ought to be able to take the oxygen masses and compare them and get a whole number ratio. So if we take 2.67, which we got from CO2, and divide that by 1.33 grams of oxygen that we got from the first, right? This should roughly equal out to a ratio of 2 to 1, which is a small whole number ratio, which is what the law of multiple proportions predicts, that the second atom should be present, and you should get a small whole number ratio if you compare the masses of the second atom in each of the compounds that are able to be formed from those two atoms. Right, so it does follow the law, right? For lack of a better expression. Questions about that? Because this strategy is applicable to any question about multiple proportions, even if you have more than one compound or more than two compounds, but sometimes you can have more, right? So the way carbon and oxygen can combine to make these other compounds, we said up here is based on the oxidation number. Here it's just based on the octet rule, the different combinations. Right, that's how you get these different compounds, because of the octet rule, which we're going to talk about later. All right. Any questions about this example? So the first part of the strategy is to find the atomic mass ratio, and then make one of those two atoms 1 gram by dividing. Right. Do the same thing for the second compound, and then you compare the masses of the second atom the one that's not 1 gram. You compare those masses to see if you get a whole number ratio. That's how you determine if something follows the law of multiple proportions. All right, let's do another one. And then we'll close out with this. Any questions about anything? I see something in the chat. All right, let's do another question. It's a little bit more involved, a little bit more nuance to it. So we said I'm gonna write this whole question out so there's no ambiguity. So just bear with me on writing this out. So this is looking at this from a slightly different perspective, and you're gonna have 3 possible compounds, right? So the mass of oxygen, come on, Russell. That combines with 1 gram. So it's giving you the fixed mass up front. And you'll get, when you have problems like this that you are trying to solve, if it's a multiple proportion problem, you'll know right away because you're gonna have ratios for multiple compounds. And you'll see as I continue to finish writing this out. So 1 gram of nitrogen. So this is my fixed mass, or 1.42, 2.28, and 2.855, respectively. So the question now is to show how these data illustrate the law of multiple proportions. So in other words, we're going to take these numbers and we're going to show whether or not the ratios of the second atom equal up to small whole number ratios. So that's what we're trying to do. So show how these data right? We're going to show how they illustrate the law of multiple proportions. So the strategy, the first part of the strategy is already done because they've already given us the fixed mass of 1 gram with nitrogen. All right. And here the ratios are already calculated, right? So we don't have to go through in this particular example and figure out use the atomic masses to figure out the proportion because it's already given. So with compound 1, let's start there. So compound 1, we have 1 gram of nitrogen is equal to 1.142 grams of oxygen. That's given right here. Right, 1 gram of nitrogen, and it says, I said 142. My bad. That should be 1.142, not 42. So 1.142. That's for compound 1. Compound 2, what's my mass ratio for compound 2? Based on the numbers that are given up top. This is always 1 gram. We want to keep that fixed. What's the other number?
.28.
Good. 2.28 grams of oxygen. Now, what about the third compound? Because we got another compound. It's all again, the strategy is to keep one of the masses fixed for one of the elements or one of the atoms. So we're going to keep nitrogen as 1 gram. Compound 3, 1 gram of nitrogen is equal to what? Anybody?
2.855.
2.8, very good. 2.855 grams of oxygen. So the first part of the question is already done, right? Because it didn't give us N and O and just say figure out the ratios, it gave us the ratios. So now the second part of this problem is what we have to do. What we have to do now is compare the oxygen masses to see if they give us small whole number ratios, right? So let's take compound 2 and compound 1 and compare them. So we're going to compare the oxygen masses. So compound 2 is, I'm just going to say C2 over C1, which is 2.28 grams divided by 1.142 grams. Is that right? Those are the numbers we had. We had compound 1 was 1.142. Compound 2 was 2.28. Somebody calculate that for me.
One 1.996.
You said 1.996. 2.28 divided by, hold up. It may have been 1.42. Let me make sure that I got the right number. It might have been 1.42. 2.28. I get something different. I get 2.5. Oh no, I get actually hold up. Say that again now. You said 1.196.
No, 1.996.
Yeah. Okay. So this is basically, we're gonna take that and round it up. You said 1.996, is that right?
Yes, sir.
To 1. So we can round that up and say that this is a 2-to-1 ratio. So again, this is a small whole number ratio. When you compare the two oxygen masses in those two compounds. Good, my fault, my bad. That's very good. So small whole number ratio. I was looking at the wrong one on my notes. All right, let's compare compound 3 to compound 1. So that's going to be 2.855 divided by 1.142. Somebody calculate that. So 2.855 divided by 1.142.
2.5.
2.5. So I get 2.5 to 1. All right. Here's for these types of problems, multiple proportions, you get to do something that you normally that you would enjoy doing, which is doing whatever you want to do, right? So we're going to take this and we're going to turn it into a whole number ratio. So if I take the top and the bottom and multiply them both by 2, what do I get? 5 to 2, is that right?
Yes, sir.
So so I can make, if I get a decimal, I can make it whole by multiplying it by some number to make it a whole number. So let me put that in here as part of the strategy. Because the goal again is to check to see if you get small whole number ratios, which you do. 5 to 2 is a small whole number ratio. All right, so top and bottom by 2, and you're going to get a small whole number ratio of 5 to 2. Now let's do the last one. Let's take the second compound 3 and compare it to compound 2. So that's gonna be 2.855 divided by, and this is grams of oxygen, divided by 2.28 grams of oxygen. What do you do?
1.25.
1.25 to 1. All right. How can I make that whole? What can I multiply by to make that whole?
4.
I can multiply both top and bottom by 4. Excellent. Who is that, by the way? Is it Camryon?
Yes, sir.
Yeah, nice work. Nice work. Put your cat, you use Cash App?
Yes, sir.
Put that in the chat. I'm gonna buy you lunch today because you've been crushing it.
Appreciate it.
I multiply both by 4. So in this case, we're gonna get a 6-to-4 ratio, which is again a small whole number ratio. So let's go back to the original question. What did it ask us? Show how these data illustrate the law of multiple proportions. So does the data match up with the law, which says that for a fixed mass of any atom of a compound, the second atom or the other atom in that compound should be present in small whole number ratios in the other compounds. Did we just prove that?
Yes.
We did.
For the last one where it says 1.25 and you multiply by 4, wouldn't it
My
be
bad.
5/4?
Yeah, 5-to-4, 5-to-4. Looking at something else. Yeah, you're right. It's 5-to-4, not 6-to-4. Make sure you fix that in your notes. And I'm gonna leave that in the YouTube video too, to make sure that folks know we ain't, bull jiving at Tuskegee. We get stuff right. So thank you for pointing that out. Yeah, it's 5-to-4. All right, we're gonna stop here. I know we went over a little bit. You can expect to see this again. We're gonna start Wednesday off with another example, and then we're gonna move on to some other atomic theory, talking about the structure of the atom and things like that. All right. Any questions? Good question, Ortega. You said, how do you choose the whole number? Are you talking about when I make 1 gram?
So like when you, at the last question, when
Mhm.
it was 1.25 over 1 times 4,
Mhm.
how do you know like what whole number to choose?
Oh, you mean to multiply that decimal by?
Mhm.
Yeah, it's not necessarily random. You just want it to be the smallest number possible. So in this case, if we multiply 1.25 times 2, that's going to give me another decimal, 2.5. So if I multiply it by 4, it'll give me 5. Right. So it's not
Okay.
necessarily random. It's just you can do process of elimination. But in this case, since it was 1.25, the smallest whole number we could get from that is 5.
Okay,
Does that
gotcha.
make sense?
Yes.
Okay. All right. Great question, by the way. I'm sure somebody else had that question but didn't ask it. So great question.
Thank you.
Mhm. All right. Any other questions about anything? Camryon, enjoy your lunch.
Appreciate it.
I don't buy Happy Meals. I normally send a pretty decent amount, so you'll be able to eat good today. But thanks for your participation, man. We need that. We need that engagement because with this virtual environment,